Let's take a look at 2.3 and we'll finish up the power rule today. A lot of the things that we're going to be doing throughout this section are going to hinge back on this power rule, so it's a really important one. And we are taking a look now at example 4. And in example 4, it gives us a position equation, which we've seen before, this type of a problem. And we're asked to find the acceleration function and the velocity function. Now, we've talked about the velocity function before. How do we find the velocity function when we're given the position function? What do we do? Yes. And we called that, Brooks, we called that our limit definition, right? Or something like that. It was the limit definition of derivative. The wonderful thing now is that we have another way of doing the derivatives that doesn't involve the limits. So the velocity is actually the same thing as the derivative. That was the word that we used. And now we have these wonderful rules, these power rules, and we've got some more coming down the line very quickly. And so this is actually asking us to find the derivative, which is, one way to do this, called s prime of t, and use the power rule, because this one will actually be able to use the power rule. Now, we have not used this phrase before. At least you haven't seen it in this class. Zach, was it you and I that were having the conversation about acceleration one day after class? So can you tell everybody what acceleration is in terms of what's going on here? Do you remember?
Yeah, it's the derivative of velocity.
Right, it's the derivative of velocity. So this is the derivative of velocity, which means it's the second derivative of the position function. So we talked about this idea of second derivatives. I can't remember which class period it was, but where we did the derivative of the derivative. We did that once before. So this is just called the second derivative. Seems like maybe it was in the last section, but maybe it was just earlier in this section. I can't remember. Yeah, it was earlier in this section. It was the last problem we did, wasn't it? Right here, where we did the second derivative right there. All right, so taking a look at this, the first thing you should notice is that number 4 doesn't quite look like we should be able to use the rule that it just said that we were going to use. It actually looks like it's a quotient, like there's division going on, right? And none of these rules over here that we just wrote down had anything to do with division. Agreed? So there must be some way to rewrite that so that we can use these rules. And in fact, there is. One of the facts that you may remember about fractions is that in order to get them into a single fraction, you have to get a common denominator, right? Right. So if you wanted to add 2/3 and 3/4, you got to get a common denominator. Well, you can actually separate fractions out back the same way as well. So if you take a look at this one, we can actually take this function and we can write each of these individual numerator pieces over the entire denominator. And for the sake of what we're doing, it will be more helpful for me to write the denominator as t to the 1/2. Is everybody good with that step so far? You don't usually use the property that direction when you work with fractions. We usually start with it in this sort of long, drawn-out sort of view that I have it now, and we squish it back together. But we can do it all out like that and separate it if we need to, and we do need to, in fact, for this one. So take a look then at the first piece. Can I rewrite this in a simpler way? What do I get when I have 4t squared over t to the 1/2? 4t to the what? No, it's 3/2. We subtract the fractions, or subtract the exponents. So the exponent on top is a 2. The exponent on bottom is a 1/2. So 2 minus 1/2 is 1.5, or 3 over 2, 3/2. And we can do the same thing for the middle one, and we're going to get what you had on that one, Zach, when you were just the one you were looking at before. So this is t on top, which is understood to be t to the 1. So when I take the 1 minus the 1/2, I get the 1/2 on that one. So this is t to the 1/2 in the middle. Now on the last piece, there isn't a t on top to sort of do this simplification of exponents with. But I could move the denominator simply up to the numerator and write it next to it with a negative exponent. Okay, does that look okay to everybody? Because once we get into that form, now I can use the power rules. It's all exactly like the power rules would allow me to use. So I can actually take and do the velocity. And the velocity, again, is this, it's just the derivative of what we just wrote up above. Okay, so you don't have to necessarily write this down. I just want to emphasize to you that it is just finding the derivative. All right, so power rule says that I'm going to do what? What will 4t to the 3/2 become? 6, and so you took the 4 times the 3 halves, right? Yeah. So let me write it out just in case somebody didn't see that initially. And then what will the new exponent be on the t? It will be 1/2, right? We have to take that power that it was before, which was 3 halves, and subtract 1, so this is now 1/2. And I've got a subtraction sign. What's the derivative of t to the 1/2?
1/2 t to the negative 1/2.
Good. Is everybody okay with that piece? The last piece is, I'm going to write down the plus 3. What I'm going to do with the t to the negative 1/2, what's that going to become?
Times negative 1/2.
Mm-hmm.
T to the negative 3/2.
So can I write this as negative 3 halves in front? Are you guys okay with that? And then t to the negative 3 halves because I subtract the exponents. All right, so let me do one simplification step here, which is the actual step that Micaiah told us originally, which was that the 4 times the 3 halves is actually 6, right? So this is 6t to the 1/2 minus 1/2 t to the negative 1/2 minus 3 halves t to the negative 3 halves. Okay, I'm almost out of space here. I'm going to try to move it up a little bit. You know what, let's do this. Doesn't like me doing that, does it? All right, that's close enough. All right, let's do the acceleration function then. So my acceleration function is going to be the same thing as taking the derivative of velocity. So I have the velocity equation right here. And it's all in the form that I actually would like it to be in order to keep going in the problem, because I've simplified just a little bit, but I've still got everything in the power form and so forth. So as I'm taking a look at the v prime of t, what am I going to get for 6t to the 1/2 to take its derivative? Right. 3t to the negative 1/2 on this piece. How about the piece in the middle?
1/4 t to the negative 3/2.
Yep, so I've got a positive 1/4 t to the negative 3/2. And the last piece over here? Positive 9/4 t to what power?
Negative 5 halves.
Negative 5/2. You may or may not see any simplification of that. Let me go ahead and take that last expression and do a little bit of rewriting as you're looking at that, so you can see how else you might see that expressed if you were looking in the back of the book or if it was asking you to simplify when you finished. So you could actually see this worked out so that each of these negative exponents goes back into the denominator, right? And each of the halves actually becomes that square root that you saw again. So this right here, this 3t to the negative 1/2 could actually be written as 3 over the square root of t, right? This piece right here is a plus with a 4 in the bottom, 1 over 4. And this is t to the 3/2, which is actually the same as t square roots of t. And the reason you can think about that is this is actually 1.5, right? So this is t with the power of 1 and t with the power of 1/2. It's one way to think about that anyway. Over here, this is a 9 over the 4 that was already here. And this would actually be, again, this is negative, so it's going to go in the denominator. This 5/2 is the same as 2.5, so you might see this written as t squared square root of t. You might even see them do what next, do you suppose? Yeah, maybe combine them all together with a common denominator. It wouldn't be too bad to do that on this one because they've all got pieces in common, right? We could actually multiply the first one here by 4t squared, the middle one by t, and the last one's already as it should be. And we can rewrite this as 4t squared plus t plus 9 over 4t squared square root t. So this would be the simplified version of the acceleration function. We can do the same thing in the middle here with the velocity function if we wanted to, right? It would work the same way. Any questions on that process here at the end? Yep, Brooks. I left it out. Let me fix that. Was that your question too, Brooks?
Well, that and also was going to ask, like, test-wise, would you want us to simplify it like that, or would you accept?
It's a really good question. That's actually where I was headed next, so you're just thinking along the same lines as I was. You've got actually a test coming up next week. Did you know that? It's not a big test. It's actually, you could call it a quiz. But it's a basic skills quiz. On the basic skills quiz, you're expected to do no simplification. Absolutely none. I don't want to see any simplification at all. And here's why. I want to actually see that you can do the process of these rules, not necessarily can you multiply certain values times fractions or can you simplify these and push them back together. So on the basic skills quiz, no, I don't want to see any simplification. On your homework, if the problem asks you to, I would expect to see that. As you get into the next lesson, I think you'll see more of where we sort of see that. On this particular one, let me tell you what well, this is kind of true in general, I guess, actually, not just true for this one. If you take a look at this question, the question started out as a single fraction all combined, didn't it? So most of the time when you're looking at values in a math problem or whatever, however the question started is how the answer should look at the end. So this answer, looking at the end like a single combined fraction, is a reasonable way to express that answer at the end because it started that way. So if the question has started out with negative exponents already in the problem, then leaving it with negative exponents in the problem at the end would be reasonable. It would make sense. So there's really nothing about the one that's in red that it's really simpler than the line above. It's just a different expression for it based on what the problem started out as. Does that make sense? So in saying that, I recognize that I have not shown you what the simplified version of this actually would look like, but are you okay with actually doing that without me showing you, or do you want to see it? What this would look like in the combined fraction form, like with a common denominator and everything. Because see, this problem asked for velocity, and it asked for acceleration. And I wrote the acceleration one out in the final form, but I didn't do that for the velocity one. I kind of didn't do it because we were in the middle of the problem and we were needing to use that unsimplified version to keep going. But at this point, going back and writing it in the simplified fraction form would be reasonable because of the way the problem started. Yes, Zach?
So on the quiz, we take the negative exponent or the exponent form. Is that okay for a question like this?
On the quiz that you take?
Yeah. Like
Yes, absolutely. On the quiz, on the test that I take, I'll be real clear how I want your answer finished.
So you could say either way.
Yeah, I could. Like I could just say in the problem, no need to simplify or something like that. I could do that on part of your test, and I probably will on part of the test. But on other parts of the test, I'm going to expect to see that you do the algebra at the end to simplify it back. I hate the word simplify, but to combine it back into something different. Because I really have a really difficult time thinking that final version there really is simpler than the one before. I don't know that it's really simpler. It just looks different, right? And so this idea of being simplified to me is a real mysterious idea, to be honest, because it kind of depends on your perspective what you mean by simpler. To me, having a fraction in the problem altogether doesn't really make it simpler. In fact, in some ways, it makes it more complicated to work with. So, kind of, yeah. And for some reason, in mathematics, we tend to not like leaving answers with negative exponents too. I don't really understand what the problem is with that, so to speak. But that's a very common kind of a description for how to leave your answer is to not leave it with negative exponents. You see that a lot in directions, I guess is my point. I don't necessarily have a problem with it. We just want to make our answer look like the original question, unless you're sort of told otherwise. And like when you do the quiz next week, when you do the quiz, I think it's Monday, you do not simplify anything. No matter how you've manipulated the problem to work with it, in the end, you will leave the problem unsimplified. So, yeah. I know that was a long way around your question. Did I answer it okay, though? Okay. All right, I think we've got another one here. Yes, all right, so this one says to find an equation of a tangent line. Now, on your homework that I handed back, some of you had this question here as well, and I know you were doing limits, and it was a little bit different on the processing of it, but on this one, what I want you to recognize is that if it asks you to find the equation of the tangent line, your answer is not complete until you actually have that equation. Some of you stopped just shy of doing that, like you found the actual derivative, but then you failed to do the last part, which was to turn it into an equation. So be real careful. Don't, especially when you're doing on a test or whatever, make sure you're looking at what you're actually asked to find and giving every piece of it. Not more than you need, but not less than you need as well. All right, so this one wants us to find an equation of a tangent line. Whenever we see that phrase, equation of the tangent line, it's asking us to find, first of all, the slope of the tangent line. And finding the slope is equivalent to finding the derivative. Now, in the two lessons you've done prior to this one, finding the derivative meant that limit definition, right? Limit of f of a plus h minus f of a over h, or some variation of that. The wonderful thing now at this point is you have a more concise way of doing that. So the computation is cleaner and quicker than it was prior to now. So when you're looking at this, the derivative is actually this power rule, because both of the pieces of this are actually written in a way that allows us to use the power rule. So taking a look at this, I've got 2x to the 3/2. What's the derivative of that?
3x to the 1/2.
Very good, 3x to the 1/2. All right, now I've got negative 3x to the negative 1/2. What's that one's derivative? X to the negative 3/2, right? So we'll have our previous exponent, which was negative 1/2, and we'll subtract 1 to get negative 3/2. Everybody good so far? So this is one of those ones where whatever simplification you do is really whatever you need to see to actually plug the value in. I don't need to put this in a clean, concise form, because that's actually not what I'm asked to find. I'm asked to find what happens when I evaluate this at x equal 4, right? So for me, it helps me to see these square root kind of things in there instead of seeing powers of 1/2. I think about square roots a little bit more clearly than I think about these powers of 1/2. So I'm going to write this as 3 square roots of x plus the 3 over the 2. And I'm going to write this as x and then square root of x. You don't have to do this. You can think of it differently, and that's okay. If you want, you could actually take your calculator at this point where we were before and evaluate. I'm okay with that. That's fine. But if I'm going to do it by hand, this is how I think about it best. So this is the actual derivative. I want the derivative at x equal 4. So I have 3 square root of 4 plus 3 over 2 times 4 square root of 4. Any questions so far? All right, so what is 3 square roots of 4? 3 times the square root of 4. I'm sorry, I said it wrong. That would be 6. Over here, I've got a 3 on top. What's on bottom? 16. So this is plus 3 over 16. And while we could, I suppose, write this as 6 and 3 over 16, you guys know that math doesn't usually leave things written in a mixed number form when we're writing equations for lines. So it's much more reasonable for us to actually write this as an improper fraction. The way that we would do that is we would figure out what is 6 times 16? Somebody have a calculator? 96 plus the 3? 99. So the slope is what we just found. Whoops. This right here, f prime of 4, this is the slope of my tangent line. But you have to be careful, right? You're not done, because they didn't ask you find the slope of the tangent line. They asked you to find the equation of the tangent line. So an equation for a tangent line actually means that I have these pieces. Some of these pieces I know. In fact, a couple of them I know. One of the pieces I don't right now yet. I know the slope. We just found out that that's 99 over 16. I also know what the x1 value is. What is it? It's 4. Good. The y1 is what I don't actually have written down or done yet. How do I find out what y1 is? Good. Plug in the 4, and then you plug it into the original equation, because the original equation actually gives ordered pairs on the curve, whatever the curve looks like. So let me actually take a moment up here, and I will do it along the top, I think. So I've got f of 4. So this is actually 2. And then I've got 4 times the square root of 4, because that's what the 3/2 power means, is I've got x and then another 1.5 x's, so a 4 and a square root of 4. And then I've got minus 3 over the square root of 4. because I've got that power of negative 1/2, which is a negative exponent, so I can put it in the denominator with a positive. All right, so what is 2 times 4 times the square root of 4? 16 minus what? Yep, minus 3/2. And if you grab your calculator, what is 16 minus 3/2 and then put back into an improper fraction? Something over 2, right? 29 is correct. So the y value right here that's missing, I'll keep it in green just to remind ourselves where it came from, is 29/2. All right, so let's write this in a clean way. I mean, this doesn't look very nice. Normally we would want this to be written as y equals. So this is y equals, I've got 99 over 16x minus 99 over 4, actually, and then plus the 29/2. If I move that to the other side. I can combine the last two together, right? So what is 99 over 4? And that's negative, and then the 29 over 2, which is positive. I'm going to have a negative. Did anyone get it? Right, so you can multiply this by 2. It is 41. 41 over 4. And most of your lines are not going to look so obscure. They're going to have smaller fractions or smaller values that you're going to be working with. But I don't want you to always think that everything I do in class being simple means all your homework will be too. Yes, Grace?
What equation did you use for getting y?
For getting y, I used the original function I was given right up here. Because whatever the function I'm given is the curve, right? So if you plug in an x, it spits you back out a y. So whatever the x value is at a specific point in time, if I plug it into the equation, I'll find the y value at that particular point on the curve. So if you're trying to find a y value, you always take the x value you're given and plug it into the original equation. Any other questions on this one?
Yeah, can you leave it in
Exactly.
point slope form, or do you want it in standard?
If the problem doesn't specify, then you could leave it. I will tell you that on the test, I'm going to ask you to put it into the y equals in x plus b form, just because I think that that simplification is important, because it at least allows you to put it into your calculator from there. Well, at the very least, moving the 29 over 2 over would. Yeah. I'll ask you to put it into y equal mx
So you'll
plus b.
specify?
I will specify that on the test, yeah. So it would be a good idea to practice a few of them like that, but if it doesn't specify that it has to be in that form, you could leave it otherwise. In fact, a couple of you left your equations from the one homework I just gave you back in another way, and I didn't take anything off for that because, again, it didn't specify. Yeah, that's a good question. Any other questions before we close this one? All right.